Now what we will do is look at the temperature dependence of doping. Okay. So first let us take a condition where we have added these, let us take an n type semiconductor again. Okay. We have added these donor dopants, right. So we have populated the semiconductor with Nd per unit volume donor dopants, and it has all created this little bunch of states at an energy level Ed, which we had found that was very close to the conduction band edge. It was about 0.1 electron volts or less, close to the conduction band edge, and all these donor atoms have got 5, they are all initially neutral, they all have 5 valence electrons because we are talking about silicon, and they are all occupying these states. Okay. So what we have shown here is that these blue circles that you see, these circles are all electrons. Okay. And what this implies, by my placing electrons on this, it implies that the 5th electron is still attached to the donor dopant. So this is still one entire species. Okay. So if you think of the donor as having say a nucleus, and it has these many electrons, and we will only show the valence electrons, the 5 valence electrons. So these 4 are going to participate in the bonding with the silicon. Okay. They are participating in the bonding with the silicon, and this entire thing together is charge neutral. Okay. But the moment this electron moves away, it is going to leave a positively charged core behind. So which is, this is charge neutral, this is an electron. So there is a negative charge here, there is a positive charge here, the entire species is charge neutral. But then the moment you pull that electron away, so let us say you have these 4 that are participating in bonding, and this is my species. The moment this electron exits, it gets into the conduction band, you leave behind a positively charged. This entire entity is now got positively charged and it is fixed, whereas the negatively charged electron is moved away. So at t equal to 0, what is being shown here is that this electron has still not moved away, and it is this electron that is being shown in this picture here. Okay. So it is that electron we are talking about. By placing an electron in these states, it is this electron that will eventually get to the conduction band that we are showing. So all these states are now charge neutral. Okay. They have got their fixed ion, but it is still not ionized, and the electron is still with the donor atom. And this happens at t equal to 0 Kelvin, and this condition is called as freeze out. So since there is no thermal energy and we are at thermal equilibrium, there is no temperature, there is no thermal energy, the electrons do not have any energy, and therefore all the electrons are sitting in the valence band, they are not able to get promoted to the conduction band. And since it is exactly 0 Kelvin, it is not only the electrons in the valence band that do not have energy to go to the conduction band, it is also the electrons present at Ed, that is with these donors, that are not able to escape the clutch of the donor atom. So it is all bound together and it is all sitting there. So the number of electrons in the conduction band is 0. So if you look at the n count, which is the electrons at E greater than Ec, which is what I am interested in for calculating the currents, is 0. Okay, so the electron concentration is 0. What is the whole concentration in the valence band? That is also 0. The P is also 0 because there are no vacancies here, all the states are filled. So this is the temperature, this is the condition at t equal to 0, and it is something called as freeze out. So I think this is a technical term, it is called as freeze out condition. So doping really does not help you if your t is equal to 0. Now let us say we start increasing the temperature, we will go from this diagram, we will move over to this diagram here. We start increasing the temperature a little. So let us say we pull up the temperature, we cross 10 Kelvin and then head to 50 Kelvin, but we are still well below 300 Kelvin, we have still not reached room temperature. Okay. So, what happens? You will find that since the temperature is now increased, the electrons do have some thermal energy. Okay. Now, since this energy gap is much smaller than that energy gap, you will find that many of the electrons that were here have all now moved up. They have taken this little thermal energy they have, and that is sufficient for them to cross this energy gap, and therefore, they have all populated the conduction band, which means this condition, these donor atoms, they moved from this state to this state at a temperature T greater than 0, and this is at T equal to 0 Kelvin. These electrons have now gotten enough energy to jump into the conduction band. It is these electrons that we are talking about. But then this is all the statistics, right. There are still many electrons that did not acquire that energy. T is greater than 0 Kelvin, a certain population. So, let us say this is the energy distribution for the electrons. So, let us say that is the energy, and that is the number of electrons. Okay. So, let me draw it better. So, let us say we are looking at a tail like this, and this is the threshold. Okay. So, it is only these electrons that can jump up from here to there. So, you still do have some donors that are not ionized, because those electrons did not statistically collect enough energy to cross this 0.1 electron volt barrier, and therefore, you do have some of the donor atoms still in this condition with the electron still bound to the donor, whereas many of the donor atoms are now ionized. They have left behind positive cores. I should have shown the positive core here. They have left behind this positive core and promoted the electron into the conduction band. So, these there are many several of them where the electron has escaped the clutch of the donor atom. Okay. So, that is the case at T equal to some temperature greater than 0 Kelvin, but less than 300. And since the temperature is still much less than 300, you do have quite a few of these donors that are ionized, but then most of the electrons in the valence band are still stuck to the valence band. You might find one or two that could statistically collect enough energy to get past the energy gap, but this gap is almost 10 times that gap, and therefore, that count is going to be very few. So, we have shown say 4 of them escaping this and maybe just 1 escaping the valence band. So, but the numbers are going to be much more different. Okay. So, that is what happens when you start to increase the temperature slowly. Some of the donors get ionized and some of them contribute to the electrons. So, what we should do to correctly show this picture is we will draw static positive charge at the locations at the donor sites where the electrons have left the donor, whereas these are all still charged neutral. Okay, these are all charged neutral sites. So, this is the correct picture, and here we have a vacancy, we have got a hole that is left behind. So, that is going to contribute to your count P. So, as we increase the temperature further, so let us start approaching 300 Kelvin, we hit say 273 Kelvin, and then we start increasing it and we start approaching 290 Kelvin, and we are in and around 300. So, in and around 300 we have a large number of electrons, okay, that have escaped the valence band and left behind holes, and these electrons have all migrated to the conduction band. The temperature is now large enough, but this temperature is much more than enough for the electrons in these donor levels to escape the clutch of the donor. And at these temperatures you should find that almost all, in fact all the donors would have ionized. If the doping is done properly, all the donors would have ionized, they would all left behind positive ion cores there, and all these electrons would have escaped. You will find now a lot more electrons from the valence band in the conduction band, and all the electrons from these donor sites now in the conduction band. Okay. So, at this temperature all donors are ionized and the semiconductor is now called extrinsic. Okay. So, when we say extrinsic semiconductor, it means that as opposed to an intrinsic semiconductor, that means it is a pure semiconductor without any doping. As opposed to a pure semiconductor, the electron population for the case of n type doping, the electron population is largely because of the donor contribution. That is, all the donors are ionized, and that is what is contributing largely to the electron count and not so much the electrons that have come out from the valence band. Okay, so that is what you mean by an extrinsic semiconductor. So, an extrinsic semiconductor is typically a doped semiconductor with all dopants ionized. Okay, so that is what is happening at T equal to 300 Kelvin. Now, let us say we continue increasing the temperature further, we push it up, we go from 300 to 400 and maybe even greater than 400 to 500 Kelvin. Okay. So, now the temperature is so large that these donors which were initially ionized have nothing more to do, they have got no more electrons to give up. So, they are not going to contribute anything more beyond your 300 Kelvin. They already gave up everything, all the electrons they had at 300. Okay, this is the maximum they could do. But now the temperature is so large that the electrons that were sitting in the valence band can now a significant number can migrate to the conduction band. Okay. So, in this condition it is the electrons from the silicon lattice, that is the valence band electrons, that are contributing most of the electrons to the N count, that is the electrons in the conduction band. The donors have already contributed everything they had and their contribution now is minimal. So, just to give you some numbers. Okay, so, let us say we put donors of 1E15 per cc. The intrinsic carrier concentration is about 1E10 per cc, and the number of silicon atoms in a silicon lattice is the order of 1E say 21 per cc. I might be an order more or order less, but so the order of 1E21 per cc. So, this is about 5 orders greater than intrinsic carrier count, and that is about 6 orders greater than the donor count, donor concentration. So, at T equal to 0 Kelvin, N was 0, P was 0, nobody contributed anything. At T equal to 300 Kelvin, in a pure semiconductor, intrinsic semiconductor, the N count would have been equal to Ni, which is 1E10 per cc. But since we have doped it with 1E15, the N count is going to be closer to 1E15, that is 5 orders of magnitude greater than what an intrinsic carrier count would have been. But now as we keep increasing the temperature, almost all the silicon atoms, that is we are talking about 1E21 or 1E22 silicon atoms are going to start giving up their electrons. So, let us say we have 1E17 silicon atoms that have given up their electrons. Okay, so, which means that the contribution of the silicon lattice to N is 1E17 and the contribution of the donors has not changed after 1E15, it had only 1E15 to give, it is 1E15. So, at lower temperatures the donor was contributing more. Okay, at lower temperatures if you look at the electron count, the donors were giving the bulk of the count towards N and the valence band was giving very little. But at temperatures that are much larger, all the donors have already given everything they had to give. So, the donor count has not changed, it is the same, okay, it is the same, but the valence band count is now suddenly increased it has become much larger, and this is the one that is contributing more. So, it is as though the silicon is behaving like an intrinsic material, because it is the electrons that are coming into the conduction band now are coming in from the valence band, and therefore, we call this operation at T much greater than 300 Kelvin as intrinsic operation. It does not mean that the semiconductor is intrinsic, this operation is intrinsic, I should call it intrinsic operation, okay, intrinsic like operation. The semiconductor is definitely doped, it is not a pure semiconductor, but if you look at the electron count in the conduction band, it comes largely from EV, because the donors have already given up everything they had, okay, and therefore, we call it as intrinsic operation. So, here what we plot is the electron concentration in the conduction band divided by the donor dopant concentration. And this is to gauge how this parameter or how this ratio varies with the temperature. Okay. So, as we saw the electron concentration, so at very low temperature, so let us call this a 0 Kelvin, okay. We do not really approach 0 Kelvin, so we start from a very low temperature. At this very low temperature, you have the conduction band edge, you have the valence band edge, and you have your donor levels, and all these donor levels have the electrons bound with the donor atoms. The temperature is too low for these donor atoms to ionize. Okay. Now, as the temperature begins to increase, the temperature is still very low for the electron in the valence band to get to the conduction band. Okay. So, the electron in the valence band does not make that jump. But since the donor level is located so close to the conduction band, the donor electrons can easily make this jump. Okay. So, we are only talking about an N type semiconductor here for in this particular plot, and we have assumed that we have doped it with the donor dopant. So, now as the temperature begins to increase a little, you find that these electrons can easily make this jump, and the electron concentration above EC. So, this is the electron concentration per unit volume at E greater than EC begins to increase. Now, as the temperature increases further, both sides start contributing electrons to the conduction band. So, you have the total number of electrons per unit volume in the conduction band to be N, and it is receiving electrons from the valence band as well as electrons from the donor sites, from the donor dopants. Okay. So, at T equal to 0, both these were 0, but as the temperature begins to increase, since the EC minus ED is very low, this contribution was significant, and you find that in all this region the donor contribution is important. Now, till a certain point, since the concentration is very low, we called this as the freeze out region. In fact, freeze out is technically when everything is 0, but we will call this entire region as freeze out. Now, the donors keep contributing. Okay. So, more and more donors keep getting ionized. So, let us say we had implanted 1E15 donor atoms per cc, donor dopants per cc. At say this temperature, let us say 100 donor dopants contributed, were ionized, and therefore, they contributed 100 electrons to the conduction band. And as the temperature increases, this contribution will significantly start increasing. Okay. So, let us say here 1E10 donors contributed, and we will reach a temperature where all 1E15 donors will contribute. Okay. So, the temperature here is large enough that all 1e15 donors have ionized and all these electrons have moved to the conduction band, leaving behind positively charged donor cores. Okay, so, these are immobile positively charged centers and all these electrons have now populated the conduction band. Now, since the temperature is large enough at this point, you will now start seeing a significant contribution from the valence band. So, there will be holes left behind and there will be some electrons that sort of migrated from the valence band to the conduction band. Okay. So, this as the temperature increases, this contribution will increase, but this contribution will increase dramatically, it will be much larger. Okay. And beyond a certain point, all the donors would have finished contributing. There are no more donors per unit volume. So, all the 1e15 donors have contributed the 1e15 electrons and the electron count in the conduction band does not increase any further. Okay. And at this point, since the N, okay, so basically what happens at this temperature is all the Nd donors, they have all ionized, they have all become Nd plus and have contributed an electron, and therefore, all the N matches the donor concentration. Okay. So, if the intrinsic carrier concentration was say 1E10, that is without doping, and the donor concentration is 1E15, this N is now going to match Nd, because the contribution from the valence band states at say T equal to 300 Kelvin is 1E10. Okay. So, 1E10 of these came from valence band states, 1E15 came from the donor states, and the summation is close to 1E15. 1E10 is 5 orders of magnitude less than the donor contribution, and therefore, N is approximately Nd. So, this is the perfect extrinsic operation. So, we are in the extrinsic operation region and therefore, N by Nd is equal to 1. And this curve remains flat for a long time, because as the temperature increases, the valence band contribution is increasing. Okay. The donor contribution is still fixed, the donors have all given up everything they have had. Okay. So, it is always 1E15, but the valence band contribution is increasing, it goes to 1E11 per cc, but the total count is still 1E15. Then the valence band contribution will increase to say 1E12 per cc, but it is still 1000 times less than the donor contribution. So, the total count is still approximately 1E15 per cc. So, this continues for a while and the curve remains flat. It is completely in this region, it is completely dictated by the donor contribution, and this is all the extrinsic region. The valence band contribution is increasing slowly, but it is still not large enough. Now, there will be a temperature where the valence band contribution now starts to match the donor contribution. So, let us say at this temperature, the donor contribution was 1E15 per cc, the valence band contribution will match this contribution, and you will start seeing the N by Nd starting to get greater than 1. So, the N has increased beyond Nd and the N by Nd curve will begin to climb up. Okay. So, beyond this point, the valence band contribution becomes greater. So, this is the donor contribution is still 1E15 per cc, there are no more donors, okay, they have given up everything, but now the valence band contribution begins to increase dramatically. So, there are many more. So, this is a very badly drawn arrow. So, what I will draw is the valence band contribution is now going to be much larger than the donor contribution. So, if the donor contribution is 1E15 per cc, the valence band will do 1E16, and at higher temperatures the donor contribution is still 1E15, the valence band will do 1E17, and now the count begins to increase. Now, you cannot ignore, you can now begin to ignore the donor contribution. So, this is going to be about 1e16 per cc, this is about 1e17 per cc and so on, and therefore, n begins to climb once more. Okay. And in this region, since it is the valence band that is contributing to the carrier, the electron count in the conduction above the conduction band, this region is called as the intrinsic region, intrinsic like operation. Okay. It is not that the semiconductor is intrinsic, as I said, it is the valence band that is contributing to the electron count as opposed to the dopant, okay, and therefore, it is like an intrinsic semiconductor. So, if we had no dopant at all, if we had let us say for example, the semiconductor was not doped at all, what would the electron count look like? Okay, so, n by nd does not make any sense. So, let us say we were to plot n, the general shape of n would so in that case we will have to redefine the y axis. Let us just do it for the sake of exercise. We will redefine the y axis in that case to n, and if we plot n versus temperature, in the case of a dopant this will now become Nd, but in the case of an intrinsic semiconductor this would have remained very low, and at a certain point this would have begun to increase. It would have crossed the 1e10 per cc mark for silicon here, and it would have continued to increase, and it would sort of asymptotically merge with this curve. Okay. So, this is what a purely intrinsic semiconductor would have done. Okay. And therefore, in this region it is as though the doped semiconductor behaves like an intrinsic semiconductor. All right. So, that is the temperature dependence of doping. Now, what we do is we want to now make a more careful count about more careful count of the number of ionized donors and more exact count of the electron and hole population. Okay. And in order to do that, we will start with the charge neutrality relation. So, as we discussed, the silicon was initially charge neutral. Okay. You have silicon atoms, some of the silicon atoms have given up an electron and they have left behind a hole. Okay. These electrons have left behind a hole. So, you do have negative freely moving negative charge and you have freely moving effective positive charge species, which are holes, and therefore, the entire system is neutral, it is not charged. And what we did now is we added a dopant. If we, for example, if we added a donor dopant, as we discussed, you have all these silicon atoms that are neutral, we have some free electrons, we have some holes, and we also have about Nd per unit volume of donors. And if these donors are all ionized, let us say some of these donors are ionized, these donors would get a positive charge and they would contribute an electron. So, you see this is charge neutral, this donor is not yet ionized, so it is charge neutral, and the entire system is charge neutral, right. So, there is no charging anywhere. Therefore, we can write a charge balance equation. All the positive charges must equal to all the negative charges, and we will take a very general semiconductor wherein we have added some donors, we have added also counter doped with some acceptors and so on. So, all the positive charges are basically the holes, okay, that is the mobile positive charge, and the ionized fixed donor charge, not all the donors, only the ionized donors. So, these are the donors, this is the donor concentration that has given up electrons. So, for example, if the semiconductor is not an extrinsic operation and if the temperature is not large enough, out of Nd, let us say alpha donors, alpha Nd remains as unionized, okay. Some portion is unionized and the remaining have ionized. So, this is the charge neutrality condition for the donors. So, this is a small fraction, alpha is less than 1. This is the fraction that has not ionized, this is the fraction that has ionized. So, when we talk about Nd plus, we are talking about this fraction. Okay. So, P plus Nd plus is equal to N, that is taken into account all these electrons plus any other existing free electrons in the semiconductor, is equal to N, which is going to have negative charge, plus the ionized acceptors. Okay, just like how we talked about donor ionization, the acceptors will also have to get ionized, which means that a neutral acceptor species will take up an electron to complete the bonding. So, let us say it takes up an electron to let me write this, go one step back. An acceptor will ionize by taking up an electron and giving up a hole, which is free to move about in the lattice. And let us say a fraction beta of these acceptors are not ionized and 1 minus beta of these are ionized and they gave up 1 minus beta holes. So, just for the sake of argument. So, we are talking about this fraction when we write Na minus. So, these are the ionized acceptor like species and ionized donor like species that are charged, and the ionized donors have got positive charge because they have given up an electron in the lattice, and the ionized acceptors have got negative charge, and therefore, you have this charge balance relation. So, now the question is, at some temperature what is the ionized donor concentration? How much of it is Nd plus at any given temperature? Can we calculate it? Can we calculate it with whatever information we have? Okay. So, if you think about let us draw this energy level, let us draw EC, EV and ED, right. So, that is where all the donors are sitting. Now, these have electrons and let us say these are the ionized species, they have given up electrons. Now, the total concentration per unit volume is Nd, that is how much we added, out of which a fraction of it has ionized. So, that is Nd plus, and that is what is needed for the charge balance. So, now the question is, what is Nd plus? How much, what percentage of Nd plus, what percentage of Nd is the Nd plus, the ionized donors? So, instead what we will do is we will try to calculate this ratio. You want to make a count, we want to be able to calculate it. So, we want to specifically calculate how much is Nd plus by Nd, that is what is the ratio of the ionized donors to the total donor concentration. Now, Nd plus by Nd, if you think about this diagram, okay, these donors are all sitting at some energy level Ed. Now, if you ask the question, what is the probability that an electron occupies these energy levels Ed? Now, you have got states inside the gap and these states are located at Ed. And how many states do we have? Since we have about Nd donors per unit volume, the state sort of scale, the number of states scales with this donor concentration. So, if you ask yourself the question as to how many electrons occupy the energy level, the states at energy level Ed, the answer is that it is the number of states available. Okay. So, we will say there are Nd states available per unit volume into the probability that an electron occupies the state, which is nothing but the Fermi function at E is equal to ED. So, this is the number of electrons occupying, number of electrons per unit volume occupying the states at ED, okay, which is effectively these states. You see electrons are occupying these states. We are interested in the states that are empty and therefore charged, okay. We are interested in those states that are positively charged, that is your Nd plus. So, we are interested in the probability that an electron does not occupy the state at Ed, which means it is the probability that a hole occupies the state at energy level Ed, that is your Nd plus by Nd. So, what is the probability that a hole occupies the states at energy level Ed? It is 1 minus f of E, it is 1 minus f of E equal to Ed. So, that is my f at E equal to Ed, and 1 minus that is essentially this term. We will divide by that factor there and you end up with this particular ratio. Therefore, my Nd plus is equal to this term here, which is 1 by 1 plus e to the power minus Ed minus Ef by kT into Nd. So, that is my number of ionized donors. So, it is this fraction. So, when we earlier mentioned alpha and 1 minus alpha, so this ratio 1 by 1 plus e to the power minus Ed minus Ef by kT is your 1 minus alpha. So, although this is the number of ionized donors, we need to be a little careful, okay. We have to make a small correction, okay, and that correction is something called as the donor degeneracy factor, okay, and this degeneracy factor has got little relation to the fact that whether it is a degenerate semiconductor or not. It need not be a degenerate semiconductor, okay. We are not interested in degenerate semiconductors in this course, I mean degenerately doped semiconductors. We are only talking about Ec minus Ef being greater than 3 kT, but despite that, while making a calculation of Nd plus by Nd, we need to attach a correction factor to this term, okay. And why do we need that correction factor? We need that correction factor because if I were to use this argument for any energy level, let us say there is some energy level located inside your lattice, I mean inside this energy gap because of some defect, okay. Now, 2 electrons could have occupied that energy level, okay. You could have plus half spin and minus half spin, but since this is a donor and the donor allowed only 1 electron occupancy and it gave up that 1 electron occupancy, okay, we have to have a correction factor of 2, and therefore, we add this correction factor by taking this answer which has come out from pure logic, okay, which is the ratio of Nd plus by Nd is nothing but the probability that a hole occupies the states at energy level Ed, which is equal to this term, which is a logically good argument, but we attach this little correction factor called Gd and you sort of insert that Gd in there, okay, and that Gd takes a value of 2, okay. And one other point is that as if you have a trap state that is sort of located, if you have these states instead of being located so close to the conduction band edge, if they were to be located a little closer to mid gap, you do not have to worry too much about Gd. You can take a value of 1 and you are quite safe with that value, okay. So, that is the count of the Nd plus, okay. Now, what about Na minus? So, let us say we have counter doped the semiconductor, we are trying to keep things very general, right. You have a semiconductor, you have added some Nd out of which some of them have ionized and you have also added some Na, out of which a few of them have ionized. So, what is this Na minus count? So, let us make a logical argument there once again. So, if you have Na minus, they are going to sit close to the valence band edge, just like how we made a calculation about how Ed is very close to the conduction band edge. The acceptor level energy levels are also very close to the valence band edge. So, they too will be about say 0.1 electron volts away. Okay. So, you have these acceptors also sitting very close to the valence band edge, and these acceptors, when they are charged neutral, they are actually empty, they only had 3 electrons at the valence shell, and they get ionized by taking an electron from the lattice. So, by taking an electron from the lattice, these acceptors are now ionized and they have a negative charge. Okay. So, whereas these are all still charge neutral. So, it is these acceptors that are Na minus, okay, and there are a total of Na acceptors per unit volume. So, we now ask the question, what is this ratio Na minus by Na? So, going by the same argument, Na minus by Na is the probability that an electron occupies the states at energy level Ea, where Ea is the acceptor energy level, and that is given by your Fermi function, that is your 1 by 1 plus e to the power Ea minus Ef by kT. But just like in the case of donors, we have a correction factor called the acceptor degeneracy factor, okay, and that is given by the symbol Ga. Now, logically one might say that Ga has to be 2, but since there are 2 EK diagrams for holes, you have these holes have got 2 different effective masses, they are called light holes and heavy holes. We use a factor of 2 times 2, which is Ga equal to 4, and we have this to be the ratio of Na minus to Na. So, we have now identified what is Nd plus and what is Na minus for any given temperature T. Okay. Now, as T keeps increasing, your Nd plus will eventually merge with Nd and Na minus will eventually merge with Na. Okay. But for any arbitrary T, this is the ratio. So, now we are all set to write a complete charge balance equation. So, what is P? P is equal to your Nv e to the power Ev minus Ef by kT, we have already discussed that. Nd plus is your Nd plus 1 by Gd e to the power minus Ed minus Ef by kT, where Gd is the correction factor. N is nothing but Nc e to the power minus Ec minus Ef by kT, and Na minus is this term. So, what we have done here is just bring all the terms to the left hand side and say that the left hand side is equal to 0. So, you have the positive charges and you have these negative charges that must balance out each other to maintain charge neutrality. Now, in the case of extrinsic operation, that is, we are talking about this region of the curve, we have gone past freeze out and we are in extrinsic operation and we have not yet reached intrinsic operation. So, we are talking about this region where all the donors have ionized and all the acceptors have ionized. Now, in this case your Nd plus is equal to Nd because this term has become 1. The temperature is so high, the temperature is so large that this term is negligible and it is mostly 1, and here too the temperature is so large that this term is negligible and it is mostly 1. So, in extrinsic operation all the donors have ionized. So, there is no ratio anymore. Okay. So, for example, sorry. So, if I were to draw the conduction band edge and the valence band edge and let us locate all the donors levels, initially all the electrons were here during freeze out, then as the temperature increased some of these electrons moved up and there were some ionized donors. So, that was my Nd plus and that was my Nd, and that was the ratio, that was Nd plus as compared to Nd. But as temperature increases, all the donors get ionized and Nd plus approaches Nd, it becomes equal to Nd. So, Nd plus is equal to Nd, Na minus equals to Na, and the charge neutrality relation, instead of having Nd plus and Na, you might as well just retain Nd and Na. Okay. So, the charge neutrality relation or the charge balance becomes this. Now, if we use this condition that Np is equal to Ni square and we are operating in extrinsic region operation, that is Nd plus is equal to Nd and Na minus is equal to Na, then this relation can be rewritten as this, because I am now representing my P as Ni square by N. Okay. So, now we can establish a quadratic equation with N. We can solve this quadratic equation and you will end up with the exact electron concentration per unit volume to be equal to this term and the exact hole concentration per unit volume to be equal to this term. Okay. So, you just solve this quadratic equation and you will end up with these two terms. So, what assumptions have we made here? We have made the assumption, the first assumption is all donors have ionized, all acceptors have ionized, cannot happen at low temperatures. This has to be at significantly high temperatures. Okay. Need not be too high, room temperature sufficiently is a sufficiently good case for this assumption. The second assumption is this mass action law holds, and this will hold when you are in thermal equilibrium and in the case of non-degenerate doping. Okay. So, this equation will hold. So, under these assumptions you can say that this is my electron concentration in the conduction band, this is my hole concentration in the valence band. Now, we can make one more assumption, okay, if these concentrations are quite large, which is if in the case of N type semiconductors your effective donor doping is so large that it goes much greater than Ni. So, Ni is in the order of, in the case of silicon, it is the order of 1E10 per cc. If let us say we are doing donor doping where Na is 0, no acceptor ions, and Nd is say 1E15, this is a reasonably good case to assume that Nd minus Na, which is basically your Nd, is much greater than 1E10. Okay. So, in that case, if you look at this quadratic equation, if you just go back, if you look at these terms. So, let us say, let us just take this particular equation there. Let us say Na was 0 or essentially Nd, let us just say Nd minus Na is very large. Okay. So, Nd minus Na is very large, which means that if you look at these two terms, Nd minus Na is much larger than Ni square. Therefore, in this term in the square root, the Ni square is negligible. Okay. We ignore that term and you end up with N is equal to Nd minus Na by 2 plus square root of Nd minus Na by 2 the whole square, which is basically again Nd minus Na by 2, which is equal to your Nd minus Na. So, that is the assumption we are making here. If in N type semiconductors, if Nd minus Na is much greater than Ni, then N is approximately Nd minus Na, and P can be calculated from the mass action law. Np is equal to Ni square, N is equal to Nd minus Na, and therefore P is equal to Ni square by N, which is Ni square by Nd minus Na. And if there is only one type of doping, so there is no counter doping, that is your Na is 0, then it is simply that N is equal to Nd, P is equal to Ni square by Nd, and equivalently for holes, if you have acceptor like doping, if P is approximately Na, N is approximately Ni square by Na. So, these are very useful relations for very quick calculations, okay, and this will be very useful for you during the assignments or tests in this course. Okay. So, with that we will conclude doping and we will start a new topic which has got to do with the mechanism by which carriers are generated, the mechanism by which temperature influences the free electron and hole generation by thermal excitation.